So we'll start with this video on YouTube. This guy does a pretty good job of explaining it. I'll put the link in the description. But what he's done is he's got this example here. So I've got A in the middle, B, C, D around the outside. What he's done with that, and we've got 40 kilos down here, and just looking at what the tension are on these, on AB and AD, we've got a 30-degree angle here. So what he's doing, he turns it into a free body diagram. Now notice what your textbook wants to do is it wants to just turn it into a vector diagram. Now, if you're allowed, I would do this because that is so much easier to look at. But I don't know if it's more simple or not. Anyway, so let's try to work out what they're doing in the textbook. So this one equals 0 and we have these three vectors up. That seems pretty straightforward. We've got these three vectors, they're not in equilibrium, so we have a force over here. So there's a resultant force. What they want you to do is break stuff up into vector components. And that's what they've done here. So I reckon it's best if we just get stuck into a question. Now this is nice, this free body diagram. So if you brought this one up to the top and then you swap these on either side, so they're going in opposite directions, that would work pretty well. But what they've done is they've turned it into this vector diagram here. So they've taken, is it TR? TR, oh, of course, yeah, tension right. So tension right is there, tension left is there, and they're going to be equal to the tension of the weight of WP, weight of the picture. I probably should have read it better before I got into it. Anyway, so we can see how that is the same as that, but we just put the vectors in slightly different positions. It really doesn't matter where you put them, so long as you put these two top to tail, because those two are going to be equal to that one. Now these two have, left has a force going to the right, right has a force going to the left. Now they're balancing each other out, those two forces. So the only ones we need to be concerned with is the downwards force of this one and the downwards force on that one. So even though they're both bigger, the sideways or the horizontal forces are irrelevant in this case because they're in balance as well, equilibrium. And that's how we, this is just demonstrating that. Here we have an advertising sign. It's hung by two cables on the ceiling of a shop. So here's the ceiling, two cables, and there's a 30-degree angle between vertical, between where the cable is and vertical. And we've got the sign and the force of the sign going straight down. It has a mass of 45 kilograms. Okay, first thing we need to do is we need to turn it into a vector diagram. Now, I wouldn't be too worried if you wanted to draw that one first, so the equivalent of that one, before turning it into that one. Just so you're in your own mind, you're quite clear. That shouldn't take very long. So you're just going to have a tension force going that way at 30 degrees, and that way at 30 degrees. And then we've got just the one going straight down. And the weight force for that one is 45 times 9.8. So we could work out the vector force, the actual vector force in that direction. So I'm assuming the tension in each cable. Yep, mate, that seems pretty straightforward. So we got the weight force going straight down. We've got tension on the right, going to the right. We've got tension on the left, going to the left. These sideways tensions are going to be equal to each other. So hopefully you're comfortable with that vector diagram. If you want, and when you watch the other video, you might want to use a free body diagram instead, because I really like the way he does it in that video. Hopefully you've been given the option to do both, because they're both as effective as each other. We've got these horizontal components, and we've got these vertical components for each of these tensions, because they're at an angle. And then we've got here, F left equals F right, so they're balancing out. So we've got R vertical plus left vertical are going to be equal to the weight of the picture. What are they calling it? A sine. That's what the S is for the weight of the sine. So you add them together. And they're going to equal 0 because they're in equilibrium. And we know that FRV equals FLV because they're the same. Same angle. Same angles, straight in the middle. And we're assuming that this sine is homogeneous to do with straight across. It's got the same mass. It's not weighted at one end or anything like that. So we can make these assumptions just over here. There we go. Those ones. Won't let me highlight them. I should learn how to do that. It would make it easier. So expand the equation to include each of the vertical forces acting on the sine. So they all equal 0. Now you need to nominate which is a positive direction and which is the negative direction. You might be using a convention of positive being up and negative being down. But they're all going to add to 0. And so we've got the mass of the sine times gravity. Now we're subbing that in. Equals that. Okay, so the mass of the sine, 45, yep, we're saying down is negative. So 45 times negative 9.8 plus 2FRV, because they're equal to each other, equals 0. We've got minus 441 plus 2 equals 0. So we switch the 441 onto the other side. Then we divide by 2. And we're going to get 220.5 for RV. Therefore, that LV is 220.5. How have I got you so far? Hopefully pretty good. Vertical, we've got horizontal, and then we got tension at the angle and the hypotenuse. We don't need to know the horizontal at this stage, or at all, because we've got two sides of a right angle triangle with an angle in there. So why are we using cosine? Hopefully you realise that, because we've got an adjacent and we've got a hypotenuse, and that means we've got to use cosine of this angle. So cos of that angle equals adjacent on hypotenuse. Adjacent on hypotenuse. So then we can pull cos theta in underneath and do the tension, because that's what we want to find. We'll put that out there. So we've got the 220.5 over cos 30, and that equals 255 newtons. And they're both the same, so they're both equal to 255 newtons. Alright, the worked example following that one, so we've got to do this one. Let's have a look at it. So we've got a beam of mass 1500. We're assuming it's homogeneous the whole way through. Geez, I don't know how well attached that is. It's attached to one corner. Anyway, so cables 1 and 2, shown in the diagram. The beam's moving up with a constant velocity. That is a red herring. Constant velocity means forces are in equilibrium, so it doesn't matter unless it's accelerating. I don't know what to do about accelerating. I'll learn that if you need me to. Okay, so constant velocity, it's a red herring, just ignore it. Calculate the tension, cable 1 and 2, ignore the mass of the cables, use G equals 9.8. Okay, so we've got this situation. We've got tension on cable 1, tension on cable 2, and the weight force going downwards. The vertical components of these are going to add up to equal the weight force. That's going to be our starting point. The horizontal components of cables 1 and 2 are equal. It's not swinging around. So let's have a look. If you want to pause it and you want to have a go right ahead from here. Otherwise, well, if you pause it and then come back, I'll walk you through it now. Alright, so they want to start with a vector diagram, adding the forces together. So even though that one is actually up there and that one is up there, don't worry about it. So we're adding them together to give this resultant force. Again, the horizontal forces are balancing each other out. All we want is the vertical force of this one and the vertical force of that one. We add them together and they'll equal the weight force. Alright, so now we turned it into the up and down components. So F1 and F2, vertical, vertical, the force of the weight multiplied by the beam. Okay, they're just saying that what I was saying before, that's just going to equal 0. Why have they got numbers there? Why? Why have they given them numbers? Where are they getting that from? They're just making stuff up. Anyway, let's just ignore let's just ignore the numbers. Maybe I've missed something. Anyway. Alright, so we've got the weight force down of the beam equals the two vertical forces added together. We know that the total force is going to be 0, and we know that these are equal. So, the force of the weight down, we're going to call that negative, equal, plus the two forces going upwards are going to be equal 0 because they're in equilibrium. So the mass of the beam times gravity plus. So beam is 1500 times negative 9.8 because we're saying down is a negative, and we add those together to equal 0. Now we know that they're equal to each other, so we can substitute in. Oh, it doesn't matter. They're doing it. So, of course, they're doing it differently to what they did in the other one. Anyway, they made it 2 times it. Okay, so we have the vertical force being 7,350 newtons on each one. Okay. Next. So now we need the triangle because we need to work out the tension on 2. So we've got the vertical component. So we got opposite on hypotenuse. Therefore, what do we got to use? We need to use sine. Okay, so here we go. Sine of theta, and theta was 60, equals opposite over adjacent, and the adjacent is what we want. So then we do a swapsies, and we get it out there, and we put the sine underneath the force, and it should come out 8490. Okay, I'll post this up, and I'll email the link to you. But what you should do is email me back some questions. You can pick ones out of the textbook because I've got access to those, and that would be good. All right, make sure you watch. Make sure you watch this video. Okay, does it differently, but I like this one. Okay.